Okay, let's begin with the prayer. In the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Amen.
Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven.
Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil.
Our Lady, seat of wisdom,
Pray for us.
in the name of the Father, and of the Son, and of the Holy Spirit. Amen. Okay, welcome to our third lecture this fall in our 2025-2026 lecture series. I'm Dr. Henry Zepeda. I am the coordinator for the lecture series this year. We will be having, after the Q&A, we will be having wine and cheese. So please stay after that and join for that. And a while after wine and cheese, we'll have time for people to talk. And then we will also have tonight some live music and waltzing. So stay around for that if that's your sort of thing. Our next lecture in the series isn't until February 13th. Our own Dr. Tiffany Schubert will be speaking, giving us a lecture. I assume that she's talking either about Jane Austen or romance in some way. So this might be a good lecture to come to in preparation for Valentine's Day. Okay. As is our custom, we start with a poem. And I thought of fitting poems, and I thought of God's Grandeur by Hopkins seemed like a good one for tonight. Okay. The world is charged with the grandeur of God. It flame out like shining from shook foil. It gathers to a greatness like the ooze of oil crushed. Why then and now not wreck his rod? Generations have trod, and all is smeared with trade, weird smeared with soil. And bears man's smudge and shares man's smell. The soil is bare now, nor can foot feel being shod. For all this, nature is never spent. There lives a fierce freshness deep down things, and those are sweats off life's best went. All morning, groundbreaking into springs, as the Holy Ghost upright or bruised, with warm breast and right wings. Thank you. Okay, for most of you here tonight, our speaker, Dr. Daniel Shields, needs no long introduction. Indeed, it's hard to even imagine Wyoming Catholic College without including the sight of him hurrying across campus in his standard outfit, cuffed jeans, Western shirt, polo tie, complete with cowboy hat. Or with seeing him enthusiastically carrying on discussions in the classroom, his office, or a Frassati lunch table about evolution, relativity, or philosophy. Dr. Shields earned his Bachelor of Arts in Liberal Arts from Thomas Aquinas College. He then went on to earn his doctorate in philosophy at the Catholic University of America, where he wrote his dissertation, Aquinas and the Kantian Principle of Treating Persons as Ends in Themselves. Dr. Shields went on to teach at Xavier University, and then for many years at the Pontifical College Josephinum in Columbus, Ohio, before coming to Wyoming Catholic College in 2021. Dr. Daniel Shields has a long list of published papers and articles on a variety of issues in ethics, natural philosophy, and metaphysics. Among these are articles on the will, happiness, infinite regresses, providence, and love. He was awarded a prize by the American Catholic Philosophical Quarterly for his paper, Everything in Motion is Put in Motion by Another, a principle in Aquinas' first way. This topic of motion, of the motion proof of God's existence, has been one that he's thought long and deeply about. He wrote a book on the subject, put out by CUA Press, Nature and Nature's God, a philosophical and scientific defense of Aquinas' unmoved mover argument. In this book, he explains the philosophical argument and puts it in light and looks at it in light of changing scientific theories throughout the history of science. Dr. Shields tonight will be speaking on a related topic, and his lecture is titled, "The Heavens Declare the Glory of God, Modern Physics and an Ancient Cosmological Argument." Please welcome Dr. Daniel Shields.
Thank you, Dr. Zepeda, for that lovely introduction. And thank you, all of you, for coming to tonight's lecture. It's an honor to be able to speak to you. And I dedicate this lecture to my mother and the memory of my father, who passed away 3 years ago and had a superb knowledge of Thomas Aquinas and of the history of science. Okay. I also want to note that when I titled this lecture, I didn't know that the readings at Mass on November 14th included as a psalm, "The heavens declare the glory of God." So I take that as a kind of providential affirmation that this is the right lecture to give today. I will begin. The heavens declare the glory of God, and the sky above proclaims his handiwork. Day to day pours out speech, and night to night reveals knowledge. There is no speech, nor are there words whose voice is not heard. Their voice goes out through all the earth, and their words to the end of the world. Thus says the psalmist, and the apostle tells us that what can be known about God is plain to them, because God has shown it to them. For his invisible attributes, namely his eternal power and divine nature, have been clearly perceived ever since the creation of the world and the things that have been made. The natural world is thus God's first book, through which he reveals his existence and wisdom and power to mankind. In the modern era, the rise of mathematical physics has sharpened our vision of the natural world, and yet we have become a people who have eyes but see not, who have ears but hear not. The God hypothesis is said to be unnecessary. Modern science can explain all that needs to be explained about the natural world. Yet we are without excuse, for the heavens still declare the glory of God, even in and through the very discoveries of modern science. In this lecture, I intend to reflect on the findings of modern physics, showing that they continue to manifest the existence of God to anyone willing to look. Oddly enough, my guiding thread will be an ancient argument for God's existence, Aristotle's proof of an unmoved mover. The argument has its roots in ancient physics and cosmology. Haven't radical changes in our understanding of physics discredited it? The principles of inertia, conservation of momentum, and conservation of energy in particular cast doubt on it. Can't motion continue forever, all on its own, without God? My answer will be in the negative. Modern science itself shows the opposite. To make my case, I will briefly outline the central version of the classical argument and then trace the history of the relevant scientific developments to the present day. Aristotle begins his proof of an unmoved mover in Book 8 of the Physics with an attempted demonstration of the sempiternity of the world. He then utilizes this supposed sempiternity as a key premise in his proof for the existence of the unmoved mover. This is very surprising to the modern reader, as we are used to thinking that the obvious way to prove God's existence is to argue that the universe must have a beginning, and that only an immaterial and eternal God could create a universe out of nothing. In any case, it would seem that we as Christians can have no use for Aristotle's proof, since it relies on a premise antagonistic to Christian belief. St. Thomas Aquinas, for example, clearly regards it as Catholic doctrine that the universe has a beginning in time. It is strange, then, that Aquinas utilizes, even champions, Aristotle's argument for an unmoved mover. His argument in the Summa Theologiae, the famous first way, is based on Physics Book 7. That argument is not the focus of my lecture. But in the Summa Contra Gentiles and Compendium Theologiae, Aquinas bases his natural theology on the unmoved mover argument from Physics 8. In the Summa Contra Gentiles, Aquinas explicitly raises the issue of the sempiternity of the world as an objection against his own use of Aristotle's argument. His response is as follows. Quote, "The most efficacious way to prove that God exists is on the supposition that the world is sempiternal. Granted this supposition, that God exists is less manifest. For if the world and motion have a first beginning, some cause must clearly be posited to account for this origin of the world and of motion. That which comes to be anew must take its origin from some innovating cause, since nothing brings itself from potency to act or from non-being to being." Aquinas' point is that clearly the universe either has a beginning or it does not. If one can show that God's existence is necessary on both assumptions, then he most certainly exists. There is no need to decide philosophically whether the universe has a beginning. Objections to the Christian doctrine that it does have a beginning, such as Aristotle's own, can be refuted, but both a finite and an infinite past are physically possible. Now, if the universe did begin, then it is quite clear that an immaterial eternal being must exist to get it started. But if the universe had no beginning, the case is not so clear. To make a really strong argument for God's existence, Aquinas prefers to proceed on the counterfactual assumption that the universe has no beginning. If God must exist even then, his existence is most certain. I won't go through the details of the argument, either in Aristotle's text or in Aquinas' reconstruction. But the basic point is this. An everlasting motion requires an everlasting mover. Only an immovable, immaterial being of infinite power could cause an infinitely enduring motion. The power of any material mover weakens over time, and a changeable mover can only cause motion for a finite time. Not even a series of movable movers, one acting after the other, could keep the universe going forever unless the whole process were sustained by an immaterial and immovable mover. Otherwise, the process would eventually grind to a halt, and the universe would remain forever motionless thereafter. Key to this argument is Aristotle's view that all bodies spontaneously travel to their natural place and condition and then come to rest, only to be moved thereafter by external agents. Aquinas follows him on this. Water, for example, flows downhill to the sea, but not uphill to the mountains. Yet water and other natural bodies here on Earth do continue to undergo motion. Water in the ocean is turned into vapor and generates rain clouds. But such motion only continues because the sun and moon travel around the earth and by their influence continually stir the pot, as it were. They bring about cycles in the seasons, weather, winds, and tides, and they cause the growth of plants, thus providing food for continued animal and human life. But since everything in motion is moved by something else and tends towards a place of rest, the sun and moon themselves cannot continue in motion forever without an external mover. Such a mover must be an immaterial being, so as not to wear out over time. Hence, only a god could keep the universe in motion forever. Otherwise, everything would find its way to its place, and the universe would remain in stasis forever after. Now, that's all well and good, one might say, but surely this argument depends on mistaken physics. Doesn't the modern principle of inertia render it possible for astronomical bodies to remain in motion all by themselves without an external mover? The principle of inertia was given by Isaac Newton in his Principia. It is the first law of motion, a cornerstone of modern physics. Newton states it as follows: every body perseveres in its state of being at rest or of moving uniformly straight forwards, except insofar as it is compelled to change its state by impressed forces. If the principle of inertia is correct, motion can continue forever without any mover to maintain it. Inertial motion is not directed towards a natural terminus in which the body rests. It continues indefinitely without any particular goal. Furthermore, Newton's third law, that for every action there is an equal and opposite reaction, requires that in any collision or interaction between bodies, the total quantity of motion is conserved. This is encapsulated in what is called the law of the conservation of momentum. So it seems that, contrary to Aquinas' argument, motion in the universe can continue forever without the aid of any cause outside the universe. In our post-Newtonian age, people tend to conceive of the universe as a collection of particles bouncing around freely in an open space, like little billiard balls, interacting through collisions and forces, endlessly moving, changing, reconfiguring. Nothing external need move the bodies in space, because nothing short of a miracle can stop them from undergoing motion. Given this basic world image, materialists argue for the existence of innumerable worlds of all different sorts in our universe or multiverse, coalescing and dissolving over vast periods of time. The empiricist David Hume reasons that even without a God to start it or sustain it, motion in the universe can continue forever. He says, "It must happen in an eternal duration that every possible order or position must be tried an infinite number of times. This world, therefore, with all its events, even the most minute, has before been produced and destroyed, and will again be produced and destroyed without any bounds and limitations. Why may not motion have been propagated by impulse through all eternity, and the same stock of it, or nearly the same, be still upheld in the universe?" Not only must motion continue forever, but it can remain orderly and beneficial, such as we observe it to be in the solar system and on Earth around us, for unimaginably vast stretches of time. After succumbing to chaos for a much vaster stretch of time, motion will again and again fall into orderly patterns. Quote, "Suppose that matter were thrown into any position by a blind, unguided force. It is evident that this first position must, in all probability, be the most confused and most disorderly imaginable. Thus, the universe goes on for many ages in a continued succession of chaos and disorder. But is it not possible that it may settle at last, so as not to lose its motion and active force? For that we have supposed inherent in it, yet so as to preserve a uniformity of appearance amidst the continual motion and fluctuation of its parts. This we find to be the case with the universe at present. Every individual is perpetually changing, and every part of every individual, and yet the whole remains in appearance the same. May we not hope for such a position, or rather be assured of it from the eternal revolutions of unguided matter? And may not this account for all the appearing wisdom and contrivance which is in the universe?" If then Newton's laws of motion are true, can any argument for an unmoved mover still be made? Could not the universe just have always existed and always been in motion with no immaterial being to sustain it? Could not the order of the world around us have arisen as a chance consequence of the necessary laws of physics? Despite its intuitive appeal, this worldview is shown to be untenable precisely by an understanding of mechanics. The key concept here is that of quantity of motion, or what we now call momentum. It is equal to the product of a body's mass times its velocity. Hume is presuming that the quantity of motion in the universe must remain constant. But according to mechanics, the sum of the absolute values of the momenta of all the bodies in any system actually tends to decrease every time there is a collision between the bodies, and an external cause is required to sustain the same quantity of motion. How does this work? Doesn't the conservation of momentum preclude such a decrease? Well, it is easy to misunderstand this law. Descartes, for example, did. In his Principles of Philosophy, he asserted that if one treats the momentum of each body as having a scalar positive value, then the sum of the momenta before a collision is equal to the sum of the momenta after the collision. This is demonstrably false, since it leads to predictions manifestly at odds with experience. Huygens, Wren, and Wallace showed in the next generation that the total momentum before and after a collision is only conserved if momenta in opposite directions are treated as having opposite signs, rather than each being taken as a positive value. The law of the conservation of momentum is true only in Huygens' sense, not Descartes'. But this law is compatible with a gradual diminishment of motion. In modern terms, the vector sum of momenta is conserved, not the scalar sum, and this is compatible with a decrease in the magnitude of all the vectors involved. For example, if two identical pendula are let go from the same height in opposite directions and repeatedly collide with each other, their momenta continually decrease. Starting with momenta of 10 and negative 10 units, for example, they could decrease to 9 and negative 9, 8 and negative 8, 7 and negative 7, etc. The total momentum at each iteration is 0, but the quantity of motion taken in a cumulative sense, the sum of the magnitudes of every vector, is diminishing from 20 to 18 to 16 to 14, etc., until it reaches 0 and the pendula come to rest. This is what is actually observed. For the outcome of even an ideal collision to be determined, more than the law of conservation of momentum is necessary. This law leaves the resulting velocities largely undetermined. The law of the conservation of momentum must be complemented by the law that the velocity of the bodies relative to each other is equal before and after the collision. But one must be careful to distinguish between elastic and inelastic collisions, and between perfectly and imperfectly elastic ones. The law of the conservation of momentum holds for any collision, but the conservation of relative velocity only holds for perfectly elastic ones. When bodies collide, they must each deform and reduce velocity rapidly so as not to interpenetrate one another. In inelastic collisions, once the velocities of the bodies have reached equality, no further change in velocity occurs. The two bodies stick together and proceed as one. Imagine throwing mashed potatoes at a lamp or something like that. That's an inelastic collision. In the case of elastic collisions, however, after reducing their velocities to equality, the two bodies spring back into shape such that some of their lost velocity is restored. Imagine throwing a basketball against a wall. The side facing the wall will squish a bit before the ball as a whole rebounds, but it quickly regains its spherical shape. In perfectly elastic collisions, all of the lost velocity is restored, and the law of conservation of relative velocity holds. In imperfectly elastic collisions, some of it is restored, but not all. Real-world objects each have their own coefficient of elasticity, somewhere between 0 and 1, which determines how much of their relative velocity before collision they will preserve afterwards. The more elastic a body is, the less motion it will lose in a collision. A well-inflated basketball is highly elastic, but it will still not rise precisely to the height from which it falls after bouncing off the court. A deflated basketball has a very low coefficient of elasticity and hardly rebounds at all from the floor. Since no real-world bodies are perfectly elastic, some motion is lost in any collision. No less a figure than Isaac Newton himself treats this as an issue having cosmological significance. In his book titled Optics, Newton suggests a remarkable cosmological argument for the existence of God, one that parallels Aquinas' motion proof. This is significant because he does so while giving full attention to the modern principle of inertia. Quote, "The force of inertia is a passive principle by which bodies persist in their motion or rest, receive motion in proportion to the force impressing it, and resist as much as they are resisted. By this principle alone, there never could have been any motion in the world. Some other principle was necessary for putting bodies into motion. And now that they are in motion, some other principle is necessary for conserving the motion. Motion may be got or lost, but by reason of the tenacity of fluids and attrition of their parts, and the weakness of elasticity in solids, motion is much more apt to be lost than got, and is always upon the decay. Newton states here that due to the less than perfect elasticity of bodies in the real world, the viscosity of liquid and gaseous fluids, and one can add the friction between moving surfaces, quantity of motion taken in a cumulative sense is always upon the decrease. Momentum is conserved only in a subtractive sense, namely that the difference between motion in one direction and motion in the contrary direction is always the same. Newton continues, seeing, therefore, the variety of motion which we find in the world is always decreasing, there is a necessity of conserving and recruiting it by active principles, such as are the cause of gravity, by which planets and comets keep their motions in their orbits, and bodies acquire great motion in falling, and the cause of fermentation, by which the heart and blood of animals are kept in perpetual motion and heat, and the sun continues violently hot and lucid, and warms all things by its light. The three laws of motion do not conserve the same quantity of motion in the universe, but the force of gravity and the cause of heat, whatever it may be, serve to keep the levels of motion up. We will take up the issue of heat shortly when we turn to thermodynamics, but in the case of gravity, motion is only added to a system as long as the bodies stand at a distance from each other. As they fall towards each other, their quantity of motion increases as the body accelerates down. But once the bodies collide and rest together, after perhaps a few bounces, all the motion generated by gravity is gone, and no potential for further motion remains. However, if inertial sideways motion is properly adjusted to gravitational centripetal acceleration, orbital motion may be achieved and maintained in continuing cycles. Can these cycles continue forever? Here's Newton's answer. It's unphilosophical to pretend that the world might arise out of a chaos by the mere laws of nature. Though being once formed, it may continue by those laws for many ages. For while comets move in very eccentric orbits in all manner of positions, blind fate could never make all the planets move one and the same way in orbits concentric, some inconsiderable irregularities excepted, which may have arisen from the mutual action of comets and planets upon one another, and which will be apt to increase till this system wants a reformation. Such a wonderful uniformity in the planetary system must be allowed the effect of nothing else than the wisdom and skill of a powerful, ever-living agent who, being in all places, is more able by his will to form and reform the parts of the universe than we are by our will to move the parts of our own bodies. Newton holds that although the laws of physics can preserve the present order in the solar system for many ages, they cannot do so forever. Irregularities in the orbits must slowly increase over time till this system wants a reformation. In fact, the moon is slowly receding from the Earth at a rate of about 3.8 centimeters per year, and the Earth's rotation is slowing down, so that in a century, a day will be 2 milliseconds longer than it is now. If disorder in the motions of the solar system must increase over time, then the present world order cannot continue forever unless God sustains it, maintaining orderly motion in the solar system. The same thing is true for the universe as a whole. If there is to be perpetual, orderly, orbital motion, God must exist to sustain it. Otherwise, one of two things will eventually happen. Either planets and stars will collide with each other and clump together as gravitational attraction wins the victory, or inertial motion will carry the day, and the planets will fly away from each other, escaping the force of gravity, which approaches zero as a limit as the bodies recede from each other. Thus, Newtonian mechanics corroborates Aquinas' motion proof for God's existence. If the universe as we know it is to continue forever, without beginning and without end, then God must periodically or continually reform it. If it had a beginning and will have an end, then God must exist to get it started. Either way, the present world order can only be accounted for if there is an immaterial and intelligent mover outside the universe as a whole and at work on it. The difference that Newtonian mechanics makes to the Aristotelian argument is only this. According to the principle of inertia, even without God's intervention, motion of some kind might continue forever. Bodies might sail off into the blackness of space, but not orbital motion of the orderly, beneficial kind that we observe. For Aquinas, however, no motion of any kind can continue forever without God's moving activity. According to the Newtonian analysis, quantity of motion in a cumulative sense diminishes in all collisions and in all movements across frictional surfaces or through resisting media. But this loss of motion is accompanied by the generation of heat, and also sometimes sound and light. By the mid-19th century, it had been demonstrated not only that heat could produce motion in turn, but that there was an exact numerical equivalence between heat and work. A definite quantity of work could generate a definite quantity of heat, and the consumption of that same quantity of heat could generate the same quantity of work. This justified the principle of the conservation of energy. Energy is defined sometimes as the ability to do work, and in its basic kinetic form, it is closely related to momentum, but also importantly different. Kinetic energy is 1/2 the mass times velocity squared. Since the velocity is squared, kinetic energy is a scalar quantity and always positive, unlike momentum, which is a vector quantity and can have a negative direction. The energy conservation principle says that the amount of energy is never diminished or increased overall in any physical process. Energy merely changes in form from potential to kinetic, from mechanical to thermal to electrical to chemical, back to mechanical, etc. Is there any need then for God to reform the world to keep it going forever, as Newton said? Or any need for an immaterial mover to sustain motion in the universe, as Aquinas held? It turns out that developments in thermodynamics once again vindicated the motion proof. The principle of the conservation of energy is the first law of thermodynamics. According to the second law of thermodynamics, in any isolated system, the amount of energy available to do work constantly decreases, or put in other terms, entropy inevitably increases. The energy that could theoretically do work still exists, as the first law requires, but it can no longer be concentrated and harnessed to act over any given distance. For this reason, no isolated system can be self-sustaining, and if there is no God, the universe is an isolated system. There is no such thing as a perpetual motion machine. Not even the universe itself is one. How does this work? Although the quantity of energy in any isolated system never increases nor diminishes according to the first law of thermodynamics, nevertheless, energy tends to find its way into thermal form due to friction, electrical resistance, the viscosity of fluids, and other such phenomena. Thermal energy can be converted back into the other kinds of energy, but only, and this is the key point, if the thermal energy is distributed at two different temperatures. Thermal energy will only do work if there is a flow of heat from a hotter body to a cooler one. But heat always tends towards temperature equalization, even when nothing is in place to harness the flow so as to do work. For example, hot coffee cools to room temperature by transferring its heat to the air. Once energy is in thermal form, and once that thermal energy exists in a state of temperature equality, that energy can no longer be used to do work. And even before temperature equality is reached, only a portion of the flowing heat can be used to do work, a portion that depends on the temperatures of the warmer and cooler bodies. With the proper machinery, some of the thermal energy flowing from the warmer body can be converted into other forms of energy, but some of it must be deposited in a colder body whose temperature is then raised. At the same time, of course, the warmer body is cooled, and so the bodies are brought towards equality of temperature. This means that energy, although constant in quantity, tends to dissipate, to become locked away and unusable in the form of thermal energy spread out in equilibrium. All physical processes progress towards a state of thermodynamic equilibrium and come to rest in it. They only move again if non-entropic energy is added from the outside. Chemicals, for example, will react in virtue of the energy stored in them, giving off heat in the process. But every reaction comes to an end once all the chemical energy is used up and the system reaches maximal entropy. Scientists of the first rank themselves drew cosmological implications from the second law of thermodynamics. In 1852, Lord Kelvin, one of the pioneers of thermodynamics, wrote that, quote, "When heat is created by any unreversible process, such as friction, there is a dissipation of mechanical energy, and a full restoration of it to its primitive condition is impossible. There is at present in the material world a universal tendency to the dissipation of mechanical energy. Any restoration of mechanical energy without more than an equivalent of dissipation is impossible in inanimate material processes and is probably never effected by means of organized matter, either endowed with vegetable life or subjected to the will of an animated creature." And in a piece from 1862, co-authored with the physicist Peter Guthrie Tate, Kelvin wrote, "The potential energy of gravitation was the original form of all the energy in the universe, and as we have seen that all energy tends ultimately to become heat, which cannot be transformed without a new creative act into any other modification, we must conclude that when all the chemical and gravitation energies of the universe have taken their final kinetic form, the result will be an arrangement of matter possessing no realizable potential energy, but uniformly hot, an undistinguishable mixture of all that is now definite and separate. Chaos and darkness as in the beginning. As surely as the weights of a clock run down to their lowest position, from which they can never rise again unless fresh energy is communicated to them from some source not yet exhausted, so surely must planet after planet creep in, age by age, towards the sun. Thus we have the sober scientific certainty that heavens and earth shall wax old as doth a garment." Other pioneers of thermodynamics to predict a heat death of the universe were Hermann von Helmholtz and Rudolf Clausius. Helmholtz was one of the first to argue for the conservation principle. Clausius was the first person to discover and clearly formulate the second law of thermodynamics. He coined the term entropy to designate the degree to which a system has undergone transformations and lost the ability to undergo further transformation. He explained the two laws of thermodynamics as follows. 1, the energy of the universe is constant. 2, the energy of the universe, entropy of the universe tends to a maximum. He elaborates in a passage worth quoting at length. That'll also give you time to admire his beard and his glasses. 1 hears it often said that in this world everything is a circuit. The same conditions constantly recur, and in the long run the state of the world remains unchanged. Consequently, it is said, the world may go on in the same way forever. When the first fundamental theorem of the mechanical theory of heat was established, it may probably have been regarded as an important confirmation of this view. Notwithstanding, the second fundamental theorem of the mechanical theory of heat, the entropy principle, contradicts this view most distinctly. The work which the forces of nature are capable of performing, and which is contained in the existing motions of the bodies which make up the system of the universe, will be gradually converted more and more into heat. The heat, inasmuch as it always tends to pass from hotter to colder bodies, and so to equalize differences of temperature, will gradually acquire a more and more uniform distribution, and a certain equilibrium will be attained. Hence, we must conclude that in all the phenomena of nature, the total entropy must be ever on the increase and can never decrease. And we thus get, as a short expression for the process of transformation, which is everywhere unceasingly going on, the following theorem. The entropy of the universe tends towards a maximum. The more the universe approaches this limiting condition in which the entropy is a maximum, the more do the occasions of further changes diminish. And supposing this condition to be at last completely attained, no further change could ever more take place. The universe would be in a state of unchanging death. Presently, the sun contains a vast reservoir of energy in the form of nuclear fuel. It converts that energy into the radiant heat of light. This energy drives the natural processes occurring on Earth. But eventually, the sun will use up its fuel and grow cold, and life here on Earth will have to end. Indeed, according to contemporary cosmology, there are actually two possible fates for the universe as a whole. Either matter and energy will eventually become so scattered that nothing can interact meaningfully with anything else anymore, and temperatures will approach a uniform absolute zero. That's the heat death proper. Or matter will collapse gravitationally and gather until it forms a giant black hole. In either case, maximum entropy will be reached. The evidence today favors the heat death scenario. Despite the conservation principle, the rise of thermodynamics did not support the contentions of Hume and others who thought that the universe could go on as it is forever in virtue of the principles of physics alone. Time is not, on the largest scale, cyclical. Rather, it has the character of an arrow. It is headed somewhere with a terminus a quo and a terminus ad quem. Aquinas' motion proof for God's existence is, as I have argued, fundamentally disjunctive, and it is as valid now as it ever was. Clearly, the natural process of the universe either has an absolute beginning in time or it does not. If it has a beginning, then an immaterial mover must exist to get it started. If it does not, an immaterial mover must exist to keep it going forever. One can formulate this as a reductio ad absurdum argument. Either the universe is an isolated system with nothing outside it to act on it, or it is an open system. Since the universe is the totality of all physical beings, being an open system would mean being influenced by an immaterial being outside it, a being not itself subject to the laws of physics. In short, God. The alternative hypothesis is that the universe is an isolated system. Now, the universe either has a beginning in time or not. If it has no beginning, an infinite amount of time has already elapsed. But since the amount of energy available to do work is always decreasing in isolated systems, if the universe is an isolated system, if an immaterial mover is not at work on it, it would have already reached the heat death, contrary to fact. An immaterial mover of infinite power would be required to preserve the universe from heat death forever. But if the universe, or at least motion within it, had an absolute beginning, this must have been caused by an immaterial mover outside it. Thus, the universe is not an isolated system, and God is at work in it. We have to address, however, yet another development in physics that challenged the unmoved mover argument. This beard might be better. In the late 19th century, the prospect of perpetual motion reared its head again with the development of statistical mechanics, due above all to the work of Ludwig Boltzmann. Boltzmann, James Clerk Maxwell, and others helped to establish the kinetic theory of gases, according to which pressure, temperature, volume, and other macroscopic measurable quantities are functions of the number, positions, and momenta of the microscopic atoms bouncing around in a gas, which cannot be directly observed or measured. Not every macroscopic state of a body is to be regarded as equally probable, because not every observable macro state can be instantiated by the same number of possible unobservable microstates, while every microstate is regarded as equally probable. For example, the same gas could occupy a volume of 4 cubic centimeters or 9 cubic centimeters. In the latter macro state, there are many, many more different microscopic configurations that the molecules of the gas could occupy than in the former macro state. And so the latter macro state is the more probable one. Over time, it is probable that any isolated system will find its way into more and more probable states. That is, into the macro states, which can be instantiated by the largest possible number of microstates. Entropy was reconceived as a measure of this probability, higher entropy corresponding to more probable macrostates. Thermal energy, understood as chaotic microscopic motion, is a highly probable and hence highly entropic form of energy. Entropy, formerly understood as a function of heat and temperature, was now interpreted as a function of the number of possible microstates available to a system. On the statistical view, it is not impossible for entropy to spontaneously decrease. That is, for a system to spontaneously bounce out of thermodynamic equilibrium, just very highly improbable. There is a possible trajectory from every microstate to every other microstates, even ones that belong to low entropy macrostates. Hence, Boltzmann argued that one should expect the universe to wind down to a condition of heat death, and then, after unimaginably vast amounts of time, to fluctuate randomly so far out of equilibrium that an orderly universe with stars, planets, galaxies, and organisms can evolve again as the universe slowly winds its way back down to equilibrium. This would go on all by itself in endless cycles, so that there could be an infinity of time past and an infinity of time future without the influence of any immaterial being. This is a refrain of Hume's view. But there are several problems with Boltzmann's worldview that have refused to go away, despite the fact that physicists and philosophers have put a great deal of effort into solving them. The first is the reversibility objection. For every configuration of particles, each with a given position and momentum, evolving from a state of lower entropy to one of higher entropy, there exists a corresponding configuration of the same particles with the same positions, but exactly opposite momenta that evolves from a state of higher entropy to one of lower entropy. One need only rotate the velocity of every particle 180 degrees. This means that if Boltzmann's statistical viewpoint gave a complete and foundational account of macroscopic behavior, it would be equally probable for systems to evolve from higher entropy to lower entropy as to evolve from lower entropy to higher entropy. This would contradict the second law of thermodynamics, about which the scientist Sir Arthur Eddington had the following to say. Quote, "The law that entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." But Boltzmann can respond by pointing out that although it is equally probable for a system to go from an entropy value of, say, 2 to 3 as to go from 3 to 2, nevertheless, if it is given observationally that a system currently has an entropy value of 3, then it is more probable that it will change to an entropy value of 4 than to change to an entropy value of 2. There are many more destination microstates in a higher entropy state than in a lower entropy state, and so many more trajectories available to the system that increase entropy then decrease it. But this just raises a further objection. If it is more likely for a state of moderate entropy to evolve into a state of higher entropy, then it is also more likely that the state of moderate entropy evolved from a state of higher entropy than from a state of lower entropy. There are many more microstates to start from in the higher entropy condition than in the lower entropy condition, and so many more trajectories that go from higher entropy to moderate entropy than from lower entropy to moderate entropy. Thus, it is also overwhelmingly more probable that any system came from a state of high entropy than that it came from low entropy. Once again, the second law would be contradicted. Rather than always increasing, or even just increasing very consistently, entropy would increase and decrease equally often. Now, Boltzmann and Hume would find this acceptable, despite the fact that all of our observational evidence points to the validity of the second law. They think of this as an illusion produced by our myopic perspective on the universe, confined as we are to the Earth and to the short span of human history. On the grand scale, the universe spends just as much time changing from higher entropy to lower entropy as it does changing from lower entropy to higher entropy. According to statistical mechanics, tiny fluctuations away from perfect equilibrium occur all the time, and bigger fluctuations are possible but correspondingly less frequent. The whole universe is just currently on the far side of a major fluctuation away from equilibrium. Entropy decreased for a while, away from its maximum billions of years ago, and is currently on its way back to the high entropy equilibrium condition. Now, not only is this pure speculation unsupported by observation, it doesn't even make sense probabilistically. Statistical mechanics requires that a larger a fluctuation from equilibrium is, the rarer it should be. If we are currently in the midst of a rare fluctuation, we should expect to find ourselves in the least rare fluctuation that is compatible with our own existence as living organisms. But as far out as we can observe in the universe, everything is very far from equilibrium. The observed entropy fluctuation, if that is what it were, is very much greater than it needs to be for us to be alive to observe it. Thus, even on statistical grounds, Boltzmann's worldview is highly improbable. But there is yet a further problem with Boltzmann's worldview. As the physicist Leo Szilard states, if we want to use the fluctuation phenomena in order to gain energy at the expense of heat, we are in the same position as playing a game of chance in which we may win certain amounts now and then, although the expectation value of the winnings is 0 or negative. The house always wins in the long run. Although there is a non-zero chance that a gambler will win, say, 36 times his money in a given play, the amount the gambler actually wins is based on how much money he bet. If he plays with enough money and for long enough, he is almost guaranteed to make some big wins. However, he is also guaranteed to lose everything eventually. He loses far more often than he wins and has less and less money to play with. Hence, his big wins get smaller and smaller in absolute value. The house always wins. In the same way, in statistical mechanics, there is a non-zero, though wildly tiny chance that particles interact in such a way that they become more organized and reduce entropy. However, the amount of macroscopically available energy that is gained for the universe depends in part on how much microscopic kinetic energy was involved in this spontaneous concourse. When the universe enters a heat death, the finite amount of thermal energy is spread ever thinner in infinite space. Thus, any given region has less and less energy to gamble with, and the payoffs of the rare wins get smaller and smaller. Barring divine intervention, entropy always wins. My claim is not that the amount of energy in the universe decreases. That would violate the conservation of energy. But that the energy density of the universe approaches 0 as a limit at infinite time. Thus, enormous fluctuations in entropy, such as would be required to generate our observable universe, eventually become not only improbable, but impossible. One could try to evade this conclusion, however, by maintaining that the energy density cannot diminish because the universe is finite in size and hyperspherical. Alternatively, one could maintain that the universe is infinite in size and populated evenly throughout with infinite matter. But the historical progression of science, once again, quickly robbed materialists like Boltzmann of this avenue of escape. To help us see this, I first note that the two theories that play the most important roles in science today, namely quantum mechanics and general relativity, both came into being in the early 20th century. They each challenge Boltzmann's materialist conclusions, but in different ways. Boltzmann's view of statistical mechanics depends upon the idea that every fundamental law of physics is time reversible. For every process that increases entropy, the laws of physics also allow an opposite process that decreases it. But one of the fundamental processes of quantum mechanics is not time reversible, namely the collapse of the wave function. But we are not equipped to deal with that large topic, so I will set it aside and turn instead to general relativity. General relativity, introduced by Einstein, provides contemporary physics with its understanding of space, time, and gravity, and as such forms the foundation of the science of cosmology. Einstein himself was an admirer of Boltzmann. In his initial application of general relativity to cosmology, he attempted to model a steady-state universe that was in fundamentally the same condition for infinity of time past and forever into the future. But he quickly realized that his own theory proved that the steady state would be one of unstable equilibrium. General relativity required that within a finite time, the universe would either collapse gravitationally or undergo runaway expansion, thus diluting into oblivion. The universe had to have a definite beginning and an effective end. According to general relativity, the fabric of space itself expands or contracts over time. Physicists consider it unknown whether the universe is finite or infinite in size. But even if it is infinite in extent, it can still expand or contract, being stretched and thinned like an infinitely large balloon. The finite density of matter and radiation within space and the finite distances between galaxies will then decrease or increase. In the years after the confirmation of general relativity, Alexander Friedmann, Father Georges Lemaitre, and Robertson and Walker developed more accurate cosmological models of the universe than Einstein's original one. According to their models, the universe is expanding from an initial state of extreme density a finite time ago. Meanwhile, Edwin Hubble showed observationally that the universe is indeed expanding and thus not in a steady state. Cosmologists such as Gamow, Dick, and Peebles predicted that the rapid expansion from the initial state would leave behind a sea of light that should still be observable today in every direction. And in the 1960s, Penzias and Wilson observed this light, redshifted to the invisible microwave frequencies. It comes at us from every direction in space. It is referred to as the cosmic microwave background. This cemented the Big Bang theory of the universe's origins. It is now commonly accepted by physicists that our universe began in a state of extremely high density and temperature about 14 billion years ago, and will eventually reach a state of heat death. General relativity requires that the universe, within a finite time, either collapse into a black hole or expand irreversibly in such a way that every galaxy becomes causally and observationally isolated from every other. In the latter case, the density of matter and radiation approaches zero as a limit, and each isolated galaxy eventually collapses into a black hole. Both of these states represent a maximum of gravitational entropy. There is no known mechanism that could reverse the process. But the general relativistic expansion of the universe also undercuts Boltzmann's theory in yet another fundamental way. insofar as it dissipates the energy involved in the interactions between particles. This requires a little explanation. Recall the ground that was covered previously in this lecture. Observable macroscopic collisions are not perfectly elastic. Some of the energy is dissipated into heat. On the dynamical theory, however, heat itself is simply uncoordinated microscopic motion. It is often assumed that microscopic collisions between atoms and molecules are perfectly elastic, so that none of the energy involved is ever really lost. But this is not actually the case. Microscopic collisions constantly redistribute the kinetic energy represented by heat. In doing so, they cause the emission of electromagnetic waves, that is, light or radiant heat, which carries away part of the energy the bodies possessed. In fact, all bodies possessing a non-zero temperature constantly emit thermal radiation across a range of frequencies, approaching more or less to an ideal black body spectrum, with an intensity and peak frequency that rises with the temperature. Radiant heat is composed of photons. Many of the emitted photons are reabsorbed by other particles, but many of them escape into empty intergalactic space. Each photon carries away an amount of energy that is proportional to its frequency. Photons traveling through an expanding space undergo what's called a cosmological redshift. The cosmological redshift lowers each photon's frequency, thus reducing the amount of energy it can deliver upon impacting with a particle. Some of these photons might never impact another particle, and thus their energy is lost. But every one of the photons that does impact a particle and deliver its energy will have undergone a redshift and will deliver less energy than it carried away. Thus, the energy density of the universe approaches zero as a limit, and hence the entropy gambler has less and less money to bet with over time. The probability of winning any given amount falls so fast that it is never even remotely likely that a significant win will be made, no matter how much time elapses. And on a Boltzmannian or Humean view, one needs not only a single big win, but a never-ending sequence of big wins to sustain the universe forever. It is thus clear that the universe cannot be self-sustaining. However, there are, and will forever be, new speculative cosmological theories that model a beginningless and endless universe. It is perfectly appropriate for scientists to think up and elaborate new and radical theories. The progress of science is aided in this way. But for every new successful scientific theory, there are thousands of completely unsuccessful ones. Neither the general public nor philosophers need take any scientific theory seriously until it makes testable empirical predictions that are confirmed. Otherwise, it is not admissible evidence in the court of best explanation. Most of what is brought forward as science in opposition to the theistic implications of cosmology belongs in this category. Now, the only new cosmological theory relevant here that has come close to passing an observational test is the theory of inflation. In this theory, the universe underwent a brief period of rapid exponential expansion in its early history. This is frequently extended to become a theory of eternal inflation, in which some unobservable part of the universe is always undergoing inflation. On that theory, the universe can go on forever without succumbing to heat death. However, three well-known cosmologists, Borda, Guth, and Vilenkin, proved in 2003 the widely accepted BGV theorem that demonstrates that no universe that on average expands over its history can be infinite in the past. It must have an absolute beginning. And the theory of eternal inflation requires that the universe as a whole expands on average throughout its history. It is important to note that Guth himself was one of the first cosmologists to propose a theory of inflation. The BGV theorem rests only on the principle that nothing can travel faster than the speed of light, a cornerstone of modern physics. Thus, eternal inflation, even if it were true, would require a beginning to the universe, and therefore the existence of God to get the universe started. The main hope that materialists have of avoiding this conclusion is that an as yet undiscovered theory of quantum gravity will provide some way out. To bring this lecture to a close, natural philosophical reflection on general observation of nature reveals that inanimate bodies in motion tend to continue on their own after they leave contact with their mover, but also that motion constantly diminishes and cannot sustain itself forever. The history of science only confirms this view. Repeatedly, new developments in science seem to suggest that motion was perpetually self-sustaining, but the finitude of motion quickly reasserted itself each time. This happened when the newly arisen principle of inertia was balanced with the observation that the quantity of motion diminishes whenever one body comes into contact with another. It happened again when the principle of energy conservation was followed immediately by the principle of entropy increase. It happened yet again when the kinetic theory of gases and statistical mechanics were developed, seeming to guarantee that energy would always remain available given long enough periods to make use of it. But quantum mechanics and general relativity came on the scene, entailing that when particles collide, they dissipate energy by releasing photons that are then redshifted into oblivion. Einstein initially thought that general relativity could guarantee an overall static universe, but it soon became clear that the universe is expanding over time and began with a Big Bang. The same dynamic will play itself out with every future development in physics. It might have seemed, in my discussion of relativity and cosmology, that I was claiming that we now know that the universe had a beginning, but this is not the case. What we know is that it cannot be in its current low entropy state if it is an isolated system with no divine influence ever acting on it. For if it was infinitely old, it would have already reached the heat death if only physical causes were at work. But we cannot prove that the Big Bang was an absolute beginning. No known laws of physics can avoid the Big Bang or connect the state of the universe at the Big Bang to a state further back in time. But it is always possible that God was at work and carried a pre-existing universe through that point in space-time. The material world is dependent upon the immaterial. The universe is dead and lifeless unless energized by an immaterial being that is not subject to the laws of physics. The universe is not a closed system. Aquinas is right. Either God sets the universe in motion, or sustains it in motion, or both. And either way, God must exist. Aquinas' unmoved mover argument is as valid as ever, except that now the empirical evidence at least suggests, but does not prove, that the universe actually had a beginning in time, just as Christians believe. Thank you.
We'll let Dr. Shields take the questionnaires, and please speak up when you ask the questions.
Jeremy.
In your lecture, you said that two outcomes are possible for the universe according to that series. One would be heat death, the other would be a total gravitational explosion. As you developed the lecture, you focused more on the heat death as being a more likely idea, and you showed sort of the implications of that for the subject of your lecture. Could you talk just a little bit about how the gravitational implosion is a possibility and what the implications of that would be for your health?
Yeah. So in general relativity, the space, the curvature of space, and whether it's going to continue expanding or decreasing. Oh, were you not able to hear the question? Okay, let me repeat it. Okay. Dr. Holmes is wondering about the other alternative fate for the universe, the black hole fate. I spoke more about the heat death than about the black hole fate. what could produce the black hole fate, and what would the implications of that be? The universe expands or contracts according to general relativity, depending on the density of matter and radiation within the universe. If the universe had a lot more matter in it than it has, that could have caused the universe to stop expanding and to start contracting, and eventually things would run into each other, and you'd gather enough mass into a small enough space to generate a black hole. The black hole is a region that has become dense enough that the gravity is so strong that not even light can make its way out of the black hole, even if it tries to go straight outwards from the black hole. So nothing inside the event horizon can ever get out again. Obviously, if the whole universe collapsed into a black hole or a collection of black holes, nothing interesting would ever happen anymore. Nothing can come out. You just have a bunch of black holes. Now, there are theories, and they may be right, that Hawking radiation comes out of black holes, but that doesn't make anything any better, because it just means that if you give the black holes enough time, eventually they will slowly fizzle out as they send out little bits of Hawking radiation over eons, until not only are there no planets and galaxies and stars, there also aren't any black holes anymore. Okay. Abenicio?
I was wondering, one of the things you said about particles colliding and emitting photons that you said, I think, redshifted to oblivion. How does that reconcile with the conservation of sheep energy?
That is an excellent question. Maybe 5 years ago, I ran into the physicist Stephen Barr at a conference, and I asked him that question. And he hemmed and hawed for a while. And then he said, "That's a very good question. Energy conservation and general relativity is a thorny issue, and energy might not be conserved." When I've looked around and tried to see what various physicists say about this, there's a disagreement about whether energy is conserved or not. They all say it all the time, except when it comes to this case. And then they say, well, some of them say it is conserved and some of them say it's not. I was trying to be more conservative and not say that it's not conserved. Because I'm kind of following Aquinas's lead. I'll take the case that's less favorable to my position and argue on that grounds. Just like he's trying to argue on the grounds of an eternal universe, which is the less favorable alternative. Oh, I'm sorry, I don't know if everybody heard that question, but when photons are sent out and carry energy away, and then the universe expands and the photons are redshifted, thus decreasing their energy, does that mean that energy just isn't conserved? Right, so that was the question I was answering. Let's see, over here.
Black holes are assumed to be a loss of not only energy but information. No loss. The only thing conserved is information. Contradicts the idea that just doesn't make sense. We have to be on the open issues. Understanding.
Yeah, but maintaining the information, even if that's true, right? This is Hawking did a lot of work on this, but maintaining the information, even if that's true, doesn't automatically mean that it's now usable energy, right? So, yeah. So you still have an end to orbital orderly motion in a universe like our own. Florian.
Thank you, Dr. Shields. I would like to know why it is a conclusion that there's a God who is the unconclusive. Isn't simply, to say, a God with gaps. Would you like me to elaborate? Or?
If you have more, sure, go ahead. Or was that it? Okay. So this isn't saying that we don't have an explanation for something, so we're going to posit God. This is saying we have well-known and well-established laws of physics that say that this is necessarily not an isolated system, right? So we're kind of positively deriving that conclusion. But to be even more fundamental about it, in answer to your question, the physics is not the heart of what's driving this argument. This argument was made as a natural philosophical argument by Aristotle and St. Thomas Aquinas. But what we're doing is asking whether developments in physics break the argument or corroborate it. And it seems very clear to me that it corroborates it. Right? But the basic principle that nature acts for an end and that mobile bodies will move in such a way that they reach some kind of terminus and then rest in it is what's at the heart of the argument from the philosophical perspective. And the physics just affirms that in spades. Let's see, Diego?
I have a question about black holes. You were saying that in black holes, gravity is such that not even light can escape the gravitational force. And if the gravitational force, as you're saying, relativity is equated with acceleration, does that mean that there's a force that could have a velocity superior to light? If light is like not even being able to escape. Does that make any sense?
I think so, but I don't think that's how physicists would think about black holes. The way they think about it is, I mean, there's so much mass there, right? That the more mass there is, the more it curves the space-time. But there's so much mass there that the space-time has been curved like all the way around in a circle, so that even a line that went radially straight out from the center of a black hole would just curve back around into the black hole, right? Because light's always going to travel on a geodesic, but every geodesic circles inside the event horizon. There's no way out. But you could think of it as that the frame is, from the perspective of some other frame, being accelerated like too fast for the light to get out. But that's not usually how they talk about it. Well, let's see. Jonathan.
Is there any way to get a sense of how far along we are in the heat death of the universe?
I think they generally think that we're something like quadrillions of years before the heat death. But don't worry, the sun will run out of fuel in only 4 billion years. And so you can have your equivalent of the heat death in 4 billion years. Yeah. BGV, Border Guth Belenken.
Things cannot be faster than this.
Okay. They require the extra premise that the universe is on average expanding throughout its history. So Jessica's asking, how do we get from nothing can go faster than the speed of light to the BGV theorem that shows that the universe would have to have a beginning? Well, the BGV theorem is not saying that the universe necessarily had a beginning, but only if the universe on average expands. And the way they get there is by saying, take some particle that's flying by, say, our planet right now at some finite speed, right? Less than the speed of light. If you traverse its path backwards, like in time, at some earlier time, it was passing some other planet, and it would have had to have been passing that planet faster than it's passing ours. Because in between the time that it passed that last planet and it's passing ours, the universe has expanded. And that expansion has, so to speak, subtracted from the relative velocity of that particle, right? So the last planet it passed, it was going faster than it is now. And if you trace it farther back in time, it was also going faster when it passed the planet before that. And if you keep going back far enough and the universe is expanding the whole time, you're eventually going to reach back to a point in time when that particle was passing some planet at faster than the speed of light. Now, there's a mathematical formulation there that makes it more rigorous, but that's the basic idea. Yeah. All sorts of. How about let's see. Looks Noah.
You said throughout your lecture, proved, I think, rather well, according to the theories of physics we have, the universe must have one of these alternatives. However, why do we take the theories of physics and the laws of physics as a constant throughout? Couldn't someone argue that, well, maybe at a different point, the laws of physics were different in such a way that it is possible for some other outcome?
Yeah, and there are people out there who argue that. There's a physicist, Lee Smolin, who argues that. But I don't find that view very plausible, because the whole procedure of science has been to observe the universe at certain places and times, and then to extrapolate outward from there and say that it works basically the same way everywhere and always. That was the whole thing about the overturning of the Aristotelian worldview and that putting in place modern science. Aristotle and that whole tradition thought that the terrestrial world just behaved differently than the celestial world, right? And physics only got off the ground when we were able to unite those two realms into a single realm, right? So it seems to me that it would be to kind of give up on the enterprise of science to start talking about fundamental laws themselves changing. But even more fundamentally than that, from a philosophical perspective, if in any of these cases we're able to grasp some kind of essence, then that is necessarily true, right? So I don't want to give up on an Aristotelian philosophy of knowledge either. Annika?
Thank you for your lecture. I've been thinking a lot about centrifugal force and general relativity and clocks, and that could possibly explain the entropy that we see, and if we're just maybe on a spinning disk closer to the center, and so we see slower, we see things as slowing down, but really it's just because of relativity and centrifugal force. Is there any idea in that?
I'm not sure quite where you're going, but I can give you this. I saw a paper come out in the last year that argued that we may well be in the center of a rotating universe. I can respect it's a scientific journal, but I don't know how that connects to our issue at hand. Do you have a way of making that connection?
Well, I was just the entropy that we're seeing, and there's not actual entropy, it just seems that there's entropy because the clocks are slowly right?
I'm not sure how to draw that conclusion. So, someone over here, I can't see who it is behind Augustine, I think. Oh, Aiden.
How are we supposed to, or how is it proven that space-time itself is the thing that expands rather than moving themselves?
Well, if the galaxies, if space itself was not expanding, then the cosmological redshift wouldn't occur. I suppose you could think of it as a Doppler effect only. Yeah, that's a good question. Oh, I see. You can have, yeah, that's actually a really good question. It takes a little bit of thinking. In general relativity, Einstein initially had wanted desperately to not have space be a thing. There were only bodies and their distances from each other and their interactions with each other. And he called that Mach's principle. There's a scientist, philosopher, Ernst Mach, who was really influential in Einstein in its early days. But Einstein had to come to grips with the fact that once he got his theory of general relativity established, it became really clear that there are so-called vacuum solutions to the Einstein field equations, where you can have a universe with nothing in it, and you can still describe the space and the time. And it also turns out that objects that move in or rotate in relation to that space act differently than rotating in relation to other bodies. So it became clear over time, although Einstein initially resisted it, that space itself is a thing, and it's described by the general relativity equations, and that it itself does expand. And universally, that's how all of the cosmologists and physicists talk about it now. Yeah. Go ahead, Philomena.
So you talked about this being the cosmos being an open system, or if it was a closed system, then ocean would either would be rest or nothing would exist at all. But how do we see, is it possible to see the divine intervention in the system as it is? Like what is sustaining ocean if it's not sustaining itself?
Well, what would it mean to see it? We certainly don't observe it directly, except those perhaps those few souls who get to actually be present when real miracles occur. But the universe looks like it had a beginning in time, and I say it looks like in a extended sense. No one was there to see it. There's no video recording of the beginning of the universe. But we have lots of evidence that points in the direction of it having a beginning. Now, as I said at the end of the lecture, maybe it doesn't, but the evidence sure suggests that. So we could say that insofar as we have evidence that the universe has a beginning, we kind of see there God doing something, getting the universe started. You could also say, and I said less about this in the lecture, that all of the evidence points that the initial conditions of the universe were extremely fine-tuned. The Nobel laureate Roger Penrose famously argued that the condition in which the universe started was so special that he can approximate that it was had the odds of 1 in 10 to the 10th power to the 123rd power of being in that condition when it started. So if that's right, we can, so to speak, see God at work in the initial conditions of the universe. Other than that, though, it seems to me that the evidence points in the direction of the universe starting out in this real special condition and just kind of slowly coasting to the heat death, so that we don't see God in normal natural processes, like intervening and like saving the energy from entropy. But from a philosophical perspective, he certainly could be doing that. And so we don't want to rule out that possibility, even though we don't see it happening. Hey, Bella?
Thank you for your lecture, Dr. Phil. I'm curious, you spoke Aristotle and Aquinas for getting to the unmoved universe. And in that, it's their metaphysics. So both of them suppose that the physics gets us so far, and then you have to do something beyond physics in order to get further. I'm wondering what the physicists who are trying to disprove the existence of God, how far they think they can go with physics, and from your perspective, with this physical evidence, what we can get to without metaphysics.
So Aquinas' and Aristotle's argument, at least the one that I was talking about, was not a metaphysical argument. But neither was it a physics argument in our sense of physics. It was an argument of natural philosophy, which is a distinct discipline from metaphysics. And it serves as a kind of bridge, or it should serve as a kind of bridge between metaphysics and empirical science. Right? Those arguments were natural philosophical arguments, but that means that they have limited conclusions. The argument shows that an immaterial, eternal being of infinite power exists, but the argument does not show that that being is pure act, or the act of existence itself, or that he created everything from nothing and sustains it at all times in existence. To get those kinds of conclusions, you'd need a metaphysical argument. But there's nothing wrong with a proof that proves some of the things that you believe about God and doesn't contradict any of the things that you believe about God, and yet doesn't prove all the things that you believe about God. Natural philosophical arguments are much more accessible to the non-metaphysically trained average person, and hence serve a really important role in the life of the mind. But the other part of your question was about physicists who don't believe in God and where they're going with things. My experience from reading the works of many physicists and cosmologists is that many of them see physics as an enterprise that is self-enclosed, and there would be something absolutely crushing to their soul if it wasn't self-enclosed. And they are absolutely unwilling to entertain that possibility. Now, plenty of them are, but plenty of them are not. And I think of it kind of in terms of St. Augustine in the Confessions, where he, up until his mid-30s, could not for the life of him even understand what it could mean for God to be immaterial. He just could not conceive of anything other than a body, right? And that impeded his approach to the Catholic Church. But then he read the books of the Platonists, and suddenly a light bulb went off, and he knew what it would mean to be immaterial, and suddenly everything like sorted itself out. Well, he had the moral problems to overcome first, but it was a major step forward. And it seems to me that many physicists and many non-scientists in our world today cannot understand what it would mean for something to be immaterial, and that's a major roadblock. Whereas I cannot remember a time in my life when I did not have a concept of immaterial being. I don't remember ever learning it. And so it's just difficult for me to think in that way. But St. Augustine, like reading his confession showed me that's real. He was a smart guy and he couldn't wrap his mind around it. Yeah.
Thank you. I have sort of a two-part question. First, when you say that when atoms collide and let off photon emissions, and you say that they redshift to oblivion, what do you mean by into oblivion? And second, does that imply a third death of the universe, where after a ridiculous amount of time, particles collide and let off enough photons that all energy is gone?
More or less. There might be vacuum energy around, but there's a lot of questions about like what vacuum energy is, how does it work, what's its value. But yeah, the photons, right, they, it's kind of a basic fact of physics that each photon has an energy proportional to its frequency, which means inversely proportional to its wavelength. The frequency of the photon goes down if the wave is stretched out, right? And as the photon travels through an expanding space, it's just stretched more and more. So the wavelength gets longer and longer. Maybe it started out as blue light, its wavelength gets stretched, and then it's red light, gets stretched some more, and it's infrared, gets stretched some more, and it's like microwaves or radio waves. There's no end where it reaches infinite wavelength, right? But the wavelength, there's no limit to how long it can get. And at some point, the wavelength is such that there's the amount of energy that that photon has is a 1/1,000,000th of what it started with, and can't really do anything. If energy has some sort of absolute like lower limit, it would hit that at some point and maybe then just disappear. But we don't know that there is a lowest like energy unit. So, Henry.
Yeah, could you say a little more about the relationship between arguments in natural philosophy, like you have up there, or like you were talking about in the argument of Aristotle from those introduced, and the science that you're talking about, and how the science, what kind of effect can the changes in the science have on the natural philosophy? How big can those changes be? What's the
Yeah, I think that's a difficult question, but a good one. On the one hand, I don't want to reduce natural philosophical arguments and conclusions to having no more than tentative probabilistic strength to them, epistemic strength. I think that the conclusions of natural philosophy can be demonstrative and true in such a way that no future experience could overthrow that because they're known with certitude. But on the other hand, I don't want to insulate natural philosophy or any branch of philosophy from developments in science as if they don't have to have any impact on how we think or the conclusions we've drawn. Because I think that's to divorce philosophy too much from experience. So my approach has been that whatever we know for certitude with natural philosophy, no development in science will ever show that it's wrong. However, developments in science could show that there's a new previously unthought of way to read the conclusions that we already drew, so that we can see it, that this new way of thinking about things that like science, developments in science has prompted us to take is both a real movement forward and yet preserves the essential core of what we previously knew through natural philosophical reflections. So it helps us to deepen our understanding of these things in surprising ways sometimes. For example, inertia, right? To realize, oh, yeah, motion does come to an end of its own in a way, but you could have this just sailing off in the blackness of space, like in a straight line with a constant velocity. But in a way, that's kind of like not moving, because nothing is really changing. It's just there, unable to interact with anything. I think that's a kind of a surprising conclusion. And then general relativity comes along and we realize, oh, that inertial motion is actually motion along a geodesic and curved space-time. Who knew that? Like, that was kind of shocking and surprising. Didn't see that one coming. Yeah. Okay, Kolya?
I just had a question about Thomas's formulation of these arguments. Because I understood you said he didn't make his most efficacious argument in the Summa. And I was curious, just trying to understand Aquinas, why he would have chosen to make an argument not based off of this Hamiltonian view of the universe in the most definitive theological treatment of the issue, and relegated it.
Yeah, that could, I could speak at great length about that, but I'll try to be really brief, and then maybe we could talk about it later in the over wine and cheese. But the first way in the Summa is a much more modest unmoved mover argument than the unmoved mover argument in the Summa Contra Gentiles, but it's placed in a series with the other 4 of the 5 ways. And it's actually meant to be read as both 5 separate arguments and one long continuous argument. And if you put together the first 3 ways, you get a conclusion that's as strong as the conclusion that Aquinas had gotten from the unmoved mover argument in the Summa Contra Gentiles, and then he carries it forward with the 4th and 5th way. But I think he consciously chose in the Summa Contra Gentiles to follow Aristotle's procedure in natural theology, and consciously chose to not follow Aristotle's procedure in the Summa Theologiae. He wanted to do something more patristic and Christian, and so he pinned most of the strength of it on the 4th way, which is similar to one of Anselm's arguments in the Monologion, not the famous one in the Proslogion, but also similar to Peter Lombard's argument, which had been taken from Augustine in the Sentences.
Okay, well, thank you all very much for coming. Please enjoy the wine and cheese. And you can dance.